Ready to share your screen?
Yes, I am. And now you should see it in presentation mode. Not yet, but now, hopefully. Oh, okay. Am I audible and everybody sees the screen?
Yes, indeed.
Yeah. Okay, well then, yeah, thanks for the invitation. I'm very happy to present here some aspects which are very tightly, very close to the source of data all our predictions are based on. That means a particular nature of clinical data from electronic health records. This short mention of disclosure of conflicts of interest. I'm a professor for medical informatics, Medical University of Graz in Austria, but I'm also a project co-leader at CBMed, also in Graz, and I'm also the head of medical research in a medium enterprise which is called Overbis in Freiburg, Germany. So coming back to the main topic of this series of talk, namely precision medicine, I think it's obvious, we have heard it in several talks, that precision medicine is data-centered. And from a, let's say, a medical perspective, there are the following interesting use cases for data-centered precision medicine, which is first of all clinical prediction, as we also have heard in the last talk, where Robert presented this model that predicts outcome of cancer or survival of cancer. But there are other use cases, such as, for instance, clinical decision support, to bring really support of clinical decisions at the doctor's workplace. Then clinical research support, which means finding out a suitable patient for trials, clinical quality assessment, which captures indicators which then are compared to certain quality benchmarks, but also not to forget enhanced clinical data use, especially optimizing the interaction between physicians and computer systems in clinical routine, where there is still a lot to do. Well, and looking at that definition, which I think is quite well known, it's important that it highlights also medical history. And this will be the focus of this talk, because often if we look at precision medicine, we focus on all the omics techniques like NGS, proteomics, metabolomics, or new imaging techniques like, for instance, digital pathology and other things. And they are, of course, extremely important for precision medicine because they generate that big data that fuels precision medicine. But we should not forget clinical data, which is not only the phenotype, that means disease, signs, symptoms, lab results, but all other kinds like environment, lifestyle, and the whole clinical history, all points of contact between an individuum and the health system. All this also matters as data input to precision medicine. And the question is, where is this data really to be found? And the question is, it is in electronic health records. And often people mix up electronic health records with clinical information systems. And there is really a big difference because the electronic health records are let's say, are the data and the structured data or the data structures within clinical information systems, so that, for instance, electronic health records can also migrate from one clinical information system to another one. And it's perhaps a little bit provocative that I put here the dinosaur to symbolize clinical information systems, but unfortunately, it's really the case that many of those clinical information systems where the legacy from the 90s, where such systems were just seen as substitutes of paper charts and not really, let's say, data containers out of which all kinds of reuse of clinical data can be supported. So this is still a big problem with clinical information systems, and therefore also with the use of electronic health records for many purposes. So they do quite well when it's just about displaying, let's say, tables of lab values or problem lists or discharge summaries to physicians and support their documentation tasks, but often it stops there, and whatsoever attempt to reuse this data poses major difficulties, mostly technical difficulties, because many EHR systems and clinical information systems are just not made for that. So, first statement, precision medicine requires precision clinical data. And many people, let's say, who were socialized in other areas, but medicine or medical informatics, medical data science, and so on. For instance, people who come from industry or from banking, from manufacturing, and so they normally assume, well, it's about health, it's about human lives, so it must be extremely precise, but this is not the case. I think we all of us who deal with clinical data are repeatedly surprised about the imprecision of this data. Yeah, and everybody know these FAIR data principles, that data should be findable, accessible, interoperable, and reusable. And this is a very nice desideratum, and I really value those principles, and I hope that this FAIR manifesto really will lead to better data quality. But we also have to take into account that when it comes to really to clinical routine data, I'm not talking about about patient data collected for clinical trials, for instance. They have to abide very, very strict quality criteria. But when it comes to using clinical data taken out of routine systems, there are lots of barriers. So the technical barrier I already mentioned, so that most clinical information systems are really not designed for data export and secondary use. So for instance, many people are surprised that while you can get good search results by web search engines, or you can search your whole set of emails, that this is not possible in most clinical information systems, not even for data of a single patient, let alone data across patients. So for instance, if you want to know how many patients you treated had some type of adverse event, you just cannot find it out. Yeah. Of course, this is also related to legal and ethical aspects, especially because it's very sensitive data. And so for many uses of patient data, you need patient consent and de-identification. If you don't have patient consent, it's often very problematic really to use this data, because de-identification is never 100%. Then a big problem is that most data is not really structured. So most data, images, but also textual data, they are really created for human use and not for machine use. And if a physician describes a clinical case, he or she normally writes it to a human with a similar background, yeah, which explains the way how these texts are written. Well, then context and provenance. This matters because clinical data are really created in very different contexts, in different data generation workflows. It matters who created these data. Also, the intent is very important. Is the intent of data creation really supplying data for a peer physician, or is the intent just to create it for some administrative process from which you don't get any feedback ever? Yeah? And then, of course, this impacts motivation, yeah? And therefore data quality. Yeah? And if you know, for instance, that certain codes are very important for billing, then you probably won't forget these codes. You will code correctly. But if there are other ones, other diseases which are considered minor diseases, for instance, diabetes mellitus type 2 or obesity or hypertension or something like that, of which you know as a physician that coding this, let's say putting this in a structured and standardized way into the electronic patient record, that this does not have any impact on the money you get for your case, then you just don't do it. Yeah, you certainly mention those comorbidity of the patient in your written summaries, but probably won't spend any extra time in coding things which do not matter for the purpose of coding, which is mostly billing. Yeah, and finally standardization, where there are two big kinds of standards. There are more standards, but I will here focus on two kinds of standards. One is standard of meaning, which I would roughly equate with ontologies, and the others are standards for information collection and exchange, which are often called information model standards. So if we look at different kinds of documentation in the clinic, we can draw this heat map. This is really purely observational and qualitative. It's not the outcome of any computation. It's just it reflects let's say the personal impression and feeling of several people. So you see, for instance, that demographics or admission data, date of admission, the service where a patient goes to, age, and so on, date of birth. This is normally very well represented in the EHR. It's complete, it's correct. It's not very granular, and it's very structured. Yeah, it's not necessarily standardized. You may have, or often it's not standardized. It depends on the local system, whether, for instance, male is encoded by 0 and female by 1 and diverse as 2, or the other way around, or it's whether it's encoded with alphabetic characters and so on. And it's very, very small volumes of data. Then administrative codes, ICD, or in Germany, for instance, OPS code, which encodes procedures. This is not very complete by the reasons I just explained. it should be mostly correct, but often it's let's say it could be better, I would say. Yeah? It's not always 100% correct. Often it's too unspecific. For instance, there is a code for the exact location of a tumor, but the physician uses the code location not specified in that instead. This is very common. Of course, it is structured, it is standardized. At least ICD is a WHO standard, and it's modified in different countries, but let's say that at least the core content is internationally standardized. So clinical lab is standardized, is structured, but often not standardized. There is, for instance, LOINC as a standard for lab observables, but it's often not used. And so you may have, for instance, in one lab system K, in the other one K+, in the third one potassium, in the fourth one kalium, and so on. Also different units of measurements, of course. Then prescriptions, often they are not complete in the electronic health record. Sometimes they are still on paper. Problem lists, they should be rather correct, because this is a very important thing clinicians look at, but often it's just text. Then clinical registry, for instance, tumor registry, often they are not filled very accurately, so that the registries themselves have to curate the data, improve the data. Findings reports should be really complete, correct, and have the granularity they require, because this is really a main communication vehicle between different physicians. And ideally, discharge summaries should be the same, but sometimes things are missed out, or sometimes things are just summarized, which is right, which is good, because, for instance, the receiving doctor doesn't want to read 10 pages. If you send them, they just won't read everything. Yeah? So it's good that it's not of high granularity, and that some things are missed out, which perhaps are not so important, so that it contains mostly those clinical facts which need to be known by the continuing care. Okay, just to add this, so the administrative codes are mostly linked to billing, at least in most countries, and yeah, problem lists, finding reports, discharge summaries are mostly text data. Well, if we have text data and we want to have high precision data, yeah, then we need to distill this data out of the source data. So we need precision extraction tools, so that from, let's say, the heterogeneous and very subjective, human-centered, language-centered representation of a clinical case, you get structured data in context. So what does it mean? So you need mechanisms to analyze automatically unstructured data, which could be images, which could be biosignals, but here I will limit myself on natural language. And for this, you need mechanisms for information extraction by natural language processing, or NLP techniques. Yeah, because as I have said, and which probably won't change, large parts of EHR content is free text. Yeah, there are people who say, well, we need to move away from free text. Everything should be structured. But there are two problems. First, you have to define information models, information structures, like you have to create, for instance, data acquisition forms, and so somebody has to do this. And then in many cases, it's just more painful and time consuming filling such forms. And often you need different forms for the same content or similar content. And so probably physicians won't do this. So, and if there is still, let's say, a field in such a form, comment, then everything which will be put into that comment field as free text, and then we haven't gained anything. It's even worse, because then the structured data may be incomplete, at least at a first glance, while perhaps important information is in the free text comment. So, but this is very controversial. To what extent really natural language documentation can be eliminated from clinical routine? And at least my opinion on that, it cannot, and it probably should not, because really natural language is our way of communication, the human way of communication. And this is very important also in the health sector. What we perhaps should try, or what definitely we should try, is that computers understand better and better our language. And this is where NLP, natural language processing, comes into the play. Yeah, and there are several kinds of natural language texts, for instance, finding reports from radiology and pathology. Yeah, so often it's really for automatic data processing even more important to look at the radiology text than the images. Of course, which does not discard the need of image analysis. Then we have progress notes, we have nursing notes, we have problem lists, and we have discharge summaries, or discharge letters, as they are often called in those countries in which these discharge summaries are sent to the patient's GP. Yeah, here's just an example, or 3 examples of free text, and you always see peculiarities of that free text, such as in this boldface example at the right-hand side of the slide, which is really full of abbreviations, acronyms. It is an extreme, I would say, telegram-style communication, which is probably unreadable even to an informed patient, sometimes also to another clinician from another discipline. But of course, from the same discipline, in this case, it's dermatology, it's about malignant melanoma, probably the dermatologist who reads it really captures the meaning in a second, much quicker than if there were a lengthy text. There are other examples, like, for instance, in the top, where you have a kind of problem list, which also has ICD codes assigned. And if you have a closer look on it, you see that many of these ICD codes really do not fully represent the text, and the other way around. And then you see also the yellowish snippet, which at least exhibits a certain structure, such as final diagnosis, history of present illness. But you cannot expect that such structures, document structures, exist. And especially you cannot expect across institutions, across countries, across disciplines. Yeah, well, what's the goal of natural language processing, NLP? So here again, this source data, and the idea is that you use all kinds of models, of rule bases, of annotated corpora, of ontologies and terminologies to distill structured meaning out of this text. here, this is just a mock-up. It's actually extremely difficult to really parse and understand such an extremely compact text. But this is at least a possible target representation, which uses codes related to an ontology, SNOMED CT, which also complete some of these codes with values, and which also give a hint to the context in which this utterance was made, which is extremely important. For instance, the last token, tumor-free, means really absence of tumor. So that means that, or better, that the lymph nodes have no lymph node metastasis, yeah, and therefore this is extremely important to capture. For instance, presence, absence, or certainty of a diagnosis, whether it's just suspected, and so on. And it doesn't stop here. It doesn't stop in a flat list, because there are many relations also between entities in such a text, and also these relations should be represented. I will show this later to you, and then we come very close to ontologies, and also many aspects will also Robert highlighted in his talk. But here now in the context of clinical documentation and clinical text knowledge representation. Yeah, here just some additional comments. Typically such text is hastily written or dictated. It's full of typos. There are transcription errors. It's telegram style. There are those short forms. There are different dialects. Just to go, for instance, this st.p dot means history of in Austria. It's not known by physicians working in Germany, so that this even within physician could lead to severe misunderstandings, because of course it's a different whether you just had a myocardial infarction in intensive care, or you had a myocardial infarction 10 years ago and are fine. Yeah, then the semantic resources you need for NLP also have to take into consideration that clinical texts are written in the official language of the country, which in most of the world is not English. Whereas most resources, or the best resources, are only available for the English language. So clinical NLP lags behind, let's say, general NLP, but also NLP based on, for instance, Medline abstracts, exactly for this reason. Yeah? And there is a really repeatedly formulated desideratum that clinical data should be shared so that they can be annotated, that they can be used for training models. But so far, this is mostly blocked by privacy concerns, yeah, and the reliability of de-identification using not only automatic means, but even using people to do this, because it's very easy to just omit, let's say, a certain annotation, and then the text remains identifiable. For instance, if there's still a zip code and, for instance, the profession of the patient, you may really de-identify it. Yeah, well, also the problem of data ownership. For instance, if you train models with data from one institution and then you reuse this model in another institution, so is there a copyright issue, and so on. Yeah, then still the adherence to standards is quite low, for instance, SNOMED CT. And there are quality issues, which I will point to briefly. And also the fact that the language of terminologies is very different from the language of clinical text. For instance, a clinician writes lung metastasis, and in SNOMED, for instance, the official label is secondary malignant neoplasm of the lung, yeah? Which is a term nobody uses. but it's a label of the terminology or ontology, because it's more or less self-explaining, but it's complicated, nobody uses it. Yeah, and then regarding the standardization of target representations, often there are competing representations of the same content. There is a low intercode agreement in experiments that it's really sometimes just 40%, even for people or graded by annotators who are experienced, just because of the fact that the terminologies are extremely fine-grained. Yeah, then you have those representations which need to represent important context features such as negation, plan, for instance, whether an operation has been done or just planned, uncertainty, and other things, for instance, family history. All these things have to be considered in the extraction process, but also in the target representation. And also there are, even with those more and more accepted resources out there, namely SNOMED and FHIR, there are more and more, or there are known overlaps between both, which should not be there. Yeah, then precision medicine requires precision representations of clinical language. Yeah, that means that we need dictionaries. We need to have resources which represent the clinician's language, not just the artificial language of ontologies. Then, as I mentioned, just here mentioning again, the need of annotated corpora, real clinical texts with concept and relation annotations. Yeah, and this precision representation of clinical language also has to take into account that there are very subtle differences in spelling, but large differences in meaning, yeah, like these examples here. Then synonyms and homonyms. First of all, those very common 2 or 3 letter acronyms, which often have 5 to 10 different meanings according to the clinical specialty. And then particularly in German text, we find a significant amount of neologisms, of newly created words, especially because of the tendency of the German language, but there are other languages also, to aggregate words to these very long words, like here botulinus toxin Vergiftung as a single word, which probably you don't find in a dictionary. Yeah. Here is just an instance of our work regarding terminology, where we are compiling clinical terms from clinical documents and mapping them to SNOMED CT code semi-automatically with several medical students involved in this, but you can imagine that it is a never-ending story. But we also use production rules to create a lot of variants, as you see here, that we have several permutations of these terms. And even using this, we do not have, let's say, F values of better than 35% when it comes to concept recognition in texts. Yeah, if we take the English SNOMED, we have the same rate. So it's more or less the same performance, but from an application point of view, it's still not sufficient. Then there are many things, as you see here, where such a terminology matching approach is completely useless, because there are so many ways to express the same meaning. For instance, whether a patient smokes or smoked in the past, and so on. And so here, for instance, we annotated lots of these text snippets, and then created annotators or trained annotators for current non-smoker, current smoker, never smoker, past smoker. And at least for current smoker, we get really a good F score, and we can say that it's really in more or less like the inter-annotator agreement on that features between human annotators. For this, we used fast text and parameter optimized shallow neural networks and also just to mention the NLP platform we are using, which is Averbis Health Discovery, which comes with a lot of built-in annotators based on Apache UIMA, and it has interfaces to import your own annotators, such as, for instance, this smoking status annotator. So finally, precision medicine requires precision standards. And if you look at standards which currently really matter internationally for representing content of the electronic health record, it's mostly FHIR, for information models, and SNOMED and LOINC for the meaning itself. So FHIR provides templates for recurring documentation needs such as condition, which is more or less the same as diagnosis, observation, procedure, medication, administration, and many more. And the ontologies provide models of meaning. I would define this as standardized formal and or informal descriptions for the types of entities that are referred to by the EHR. This is often seen differently, and people mix up data with the things data point to. But this is very important to use these standards properly to understand that the first type, information models, are models of information. And these models of information refer to or are about entities of meaning provided by ontologies. So we can also say that ontology IDs provide standardized meaning for the patient-specific instantiations of FHIR or more generally information model resources. So far so good, but if we look more closely at many content of these standards, the desideratum that standards should have precise definitions is really not fulfilled, which you see in simple things like the definition of very fundamental and basic concepts such as condition in FHIR, and it is defined, condition is defined as a clinical condition, problem diagnosis, and so it's really not clear. It's very, very fuzzy, a concept that has risen to a level of concern. SNOMED is not better. That, for instance, you find things like what is a clinical finding, which, by the way, findings aggregate injuries, signs, symptoms, disorders, etc., or even non-pathological things like hair color or number of pregnancies. And again, you have things like they represent the result of a clinical observation, blah, 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 and includes, and then there are some examples, but it's really not a clear-cut definition. And it's quite problematic, and this became obvious in a group I participate, which is about SNOMED CT translation to German, where it's a real problem having those ill-defined terms and translating them to another language. Well, SNOMED excels, I would say, by its description logics, axioms, so that they formally define things like appendicitis in a computable way, like also Robert showed it. So it's the same language, it's EL++. And then Well, it's really great, yeah. But if you look more closely, for instance, at how appendicitis is defined, yeah, then you find a relation called row group, which nobody can really at SNOMED give a clear definition what it means. Yeah, it's a kind of pseudo operator, but which is not part of the description logics syntax and semantics. And so on the one hand, you have this formal representation, which is very useful also for certain reasoning tasks. But again, if you compare it to the claim that precisions should be precise, this is not the case. And then there are many, many, many other definitions which are just other parts of SNOMED which are just taxonomies of terms. Yeah, and for instance, you have a term or class called minor, and a subclass called adolescent or infant. Yeah, but there's no definition at all. That you should expect that as it is a standard, it should standardize the age interval. Yeah? Whether a 12-year-old is still a child or already an adolescent, and so. But there are many things you won't find it. Then standards should deal with the problem that one and the same meaning can be encoded differently. For instance, you have a text here, text 1. I translate: in the nail of the right great toe, Candida species were found as cause of infection. I think you can imagine this even not being a doctor. A physician would probably write Candida onychomycosis, right great toe. Yeah, these two snippets mean exactly the same thing. Yeah, and here, at least in theory, and I don't know real practical applications for this, but in theory, description logic's foundation should be able to, and you can show it with a classifier and it works, yeah. Given that the extraction step really works and then mapped to those SNOMED concepts, yeah, that then you can state equivalence between these two very, very different textual renderings of the same thing. Yeah. But of course, this requires that your system supports description logic's reasoning, and it also requires that the extraction works as expected. And finally, we have things like that. And just coming back to the problem with the very low inter-annotator agreement we observed, and look at that. This is how SNOMED represents anxiety, pain, fear, panic, and so. And really, you see sometimes very similar things, like, for instance, anxiety state or being worried or fear or anxiety and fear in different places. Yeah? And what is really needed for really supporting concept mapping, concept retrieval especially, is to have some notion of similarity between instances of different but similar concepts. And this is a big problem of large ontologies and terminologies. So those semantically close undefined classes, and you run into severe problems if you want to translate this to a different language. Yeah, and here I see a real potential for using graph embedding. Yeah, but in this case, really driven by real data, so that at least for a certain domain represented by a certain corpus, you would then find out that really fear and anxiety is practically the same. And so that you, if you if you search for FHIR, you also get patient records annotated with anxiety. So which are the take-home messages of this talk? Well, clinical data are overly heterogeneous. Much of the information in clinical information systems need to be extracted from free text and not of very nicely written free text. NLP-based information extraction requires costly resources, which is also difficult because of the many different languages in which clinical data are held or clinical records are held. And therefore, also the clinical texts have to be from that particular language, and it needs to be openly accessible in order to create the resources you need, such as dictionaries and annotated corpora. And precision medicine needs precision information extraction tools, precision language resources, and precision semantic standards. And for each of these three things, there is still a long way to go. Thank you very much.
Thank you, Stefan. It's a very interesting talk for me. We were talking with the hospital about essentially this task just this morning. Are there any questions from the audience? I can see some hands up, but locating who they are, it's going to take me some time.
Stefan, if you can put down the slides.
Yeah, sorry. Yeah.
And share, yeah.
That's
Sonam Kumar.
So, okay, now. Okay.
Sonam Kumar has a question. Can we unmute him?
Yes, I already allowed him the mic. Sonam, you can unmute yourself.
Yeah, am I audible?
Yeah.
Yeah, so thanks for the great talk. And throughout the talk, I was kind of trying to find out what is the difference between the personalized medicine and precision medicine. I mean, what is the role of pharmacogenomics in precision medicine? That is one of the biggest questions that I was having in my mind. And also in the role of precision medicine in mood disorders. There's a lot of questions that are plugging in my mind. But relevant to this talk, probably the question that I would want to ask is regarding the handwritten medical text that is available all over. So whenever we go to the doctor in some clinic, they give us a prescription, they write whatever the presenting symptoms are and the names of the drugs and advice. So if we could have a good machine learning or a deep learning algorithm which would try to read text from those prescriptions, we could have a really big database of healthcare, so which could probably help us in precision medicine. Now the problem is that there is a difference in handwriting. There is a difference of how different types of clinicians write their corresponding medical texts. So how would we go about with it? Because the population of the world is increasing, and there are like the third world countries and the countries which are quite developing countries, they have got huge population, and we have got a lot of medical texts that we are not being able to do anything about. So how would we go about with this?
Yeah, thanks a lot. This is really not limited to developing countries. If you go to a GP office of let's say clinician or physician of my age and or older, then it's very common to see really stacks of handwritten charts. The problem with handwritten prescriptions is it's a real patient safety issue. And so the question is really, should we concentrate forces to really stop that handwritten that practice, or should we really concentrate our forces on improving handwriting recognition, I'm not sure. I'm optimistic, and I hope that in the area of medicine, handwriting will slowly disappear. On the other hand, there are efforts on handwriting recognition, which is especially important also, for instance, for historians or people who really deal with old data. And perhaps it would be good to wait a little bit until the recognition rate is higher, such as also with OCR. If you compare the outcome of OCR now from 10 years ago, it has really improved a lot. So I have no very clear opinion on that, at least here in Germany and Austria. I would just say let's hope for a biological solution, that in the sense that the old doctors retire and the young doctors perhaps do not even write by hand in their daily practice. So this is one thing. And what you asked before, it was about pharmacogenomic, or was it just the introduction to the problem to have prescription data which are not really processable because they are handwritten? Was this the main focus on your question on pharmacogenomics?
Yeah, my main focus was about the medical texts, because you see the problem is really big, and I think reading of texts has advanced quite a lot, as you have mentioned about OCR, and also image recognition has gone too far. Google Lens and other apps, they have developed technologies in which they see a little part of the image and then they can come up with a very nice result. So I'm quite optimistic about the second option that you had posed. Thank you.
But there's another problem. What I have seen with handwritten medical text, that all that idiosyncrasy you have also with machine-written text, that you have lots of abbreviations, especially for those nodes clinicians write for themselves, namely in their practice, in their office, where they don't need to share with other people those notes. They come up with so crazy idiosyncratic symbols and abbreviations that so the task is not resolved with handwriting recognition. Of course, you should assume when the text is written for a pharmacist, then it's better. Quite sure. Yeah, it could be good to collect a corpus of images from prescriptions. Just you can make it with your phone and then ask many people, make lots of pictures of your prescriptions and then build a corpus. But of course, you also have the privacy problem, and also often in the same unreadable way, like perhaps the drug is written, also the patient name is written, and you have again the problem with privacy. Okay, but I stop here. There are other questions.
Thank you very much. I can see there's another couple of hands up, but we are a bit short of time, so we'll move on to the third